This is the Trigonometry, chapters 5 through 6 practice exam. So this first question asks us to prove that sine squared x times cotangent squared x plus 1 is equal to 1. So the strategy with these is always going to be to work on the more complicated side. So in this case, this is obviously our more complicated side. So the first thing I notice is that this sine squared can be distributed. So if I do that, I end up with this, sine squared cotangent squared plus sine squared. And then this piece of it looks like it can still be simplified. So instead of cotangent squared, I'm going to rewrite that because cotangent is equal to cosine over sine. And you may notice that in that case, the sines are going to cancel. And we are left with cosine squared plus sine squared, which is clearly equal to 1. And so we've proven it. This next one, we're going to follow a very similar procedure. So again, we're going to work on the more complicated side, which looks to me like it's this side. So just like last one, actually, the first thing I'm going to do is distribute. And when I do that, I get sine x secant x plus sine x cosecant x. And both of these look like they can be simplified a little bit more. So instead of secant, I'm going to write, well, secant is 1 over cosine. And then over here, I'll leave sine alone because sine is very common. We usually don't change sine into anything else. But cosecant is going to be 1 over sine. And then here, you might notice we've got sine and sine. Those two are going to cancel. And then these first two multiply together to give us sine over cosine. That's just a 1. And of course, sine over cosine is just tangent. So we have proven it. For number 3, again, we're going to work on the more complicated side, which looks to me like it's this one. And in the previous two and in this one, our first strategy is going to be use algebra tricks. So in the previous two, we distributed. In this one, I'm going to add fractions. So to add fractions, obviously, we need a common denominator. And these two denominators are pretty different. So what I'm going to have to do is, or at least they're pretty different in terms of denominators, in terms of multiplication and division. So what I'm going to have to do is multiply this first one by 1 minus cosine x on the bottom and the top. And I'm going to have to multiply this second one by 1 plus cosine x on the bottom and top. And that will give me common denominators. When I do that, I'm going to have 1 minus cosine x over, and you may notice this is a difference of squares. 1 plus cosine x times 1 minus cosine x is going to be 1 minus cosine squared x. So I'll just go ahead and multiply those two together. And then we can combine these into one fraction. And normally for proof structure, you really want to line up your equal sign on top of each other, but I don't have the space to do that, so I'm just going to do it in one line. But I can add these together. 1 minus cosine plus 1 plus cosine is just going to be 2. And we're going to have 2 over 1 minus cosine squared x. Now at this point, I'm going to take a look at what I'm aiming for, and I'm aiming for cosecant. Well, cosecant I know is just 1 over sine. So what I'm going to do is try to rewrite this in terms of sine. And this denominator looks a lot like, well, it actually is. It's sine squared. Because you may remember from the Pythagorean formulas, sine squared x is equal to 1 minus cosine squared x. So I'm going to make that swap. This is the same as 2 over sine squared x, which basically just gets me to my conclusion. 2 over sine squared x is the same as 2 cosecant squared x. So I'm done. For this one, number 4, we're not given very specific instructions, like exactly how to find this sine of 15 degrees. And there's actually multiple ways. You can do angle subtraction, like 15 degrees is 45 minus 30, or you could do a half angle formula because 15 degrees is half of 30. I prefer the addition and subtraction formulas, but it doesn't really matter. So I'm going to use this. I'm going to say that sine of 15 degrees is equal to the sine of 45 degrees minus 30 degrees. And then I'm going to turn to my identities. So I've saved my identity formula sheet at the bottom of this document, and you should keep it on handy when you're solving all of these problems. But looking through it, let's see. Okay, here it is, 45 degrees minus 30 degrees, and we're looking for sine. That would be this guy. So what I'm going to do is I'm actually just going to copy this identity, and I'm going to put it up next to the problem I am currently working on. So we've got this identity, and as you can see, it matches up pretty nicely. We've got sine of some angle minus another angle. So literally all I'm going to do is replace theta with 45 degrees, and I'm going to replace psi with 30 degrees. So I will have sine 45, sine 30 minus cosine 45 degrees, sine, oops, I wrote this one wrong, didn't I? There we go. Sine of 30 degrees. Okay, and when I do that, I can just plug everything in now. Let's see, sine of 45 degrees, well, that's just root 2 over 2. And then let's see, cosine of 30 degrees. If you need, you can sketch it. But 30 degrees is this one. It's 30, 60, 90 triangle. Cosine is the long side, so that's going to be root 3 over 2. And we've got minus cosine of 45 degrees is also root 2 over 2. And then sine of 30 degrees is going to be this triangle again, but it'll be the y side, so that gives me 1/2. And when I simplify this a little bit, I get root 6 over 4 minus root 2 over 4. And since those have the same denominator, I can just write them as one fraction. Root 6 minus root 2 over 4. And there's not really a good way to simplify this, so we'll just leave it. That's the answer. It's the exact value of sine of 15 degrees. This next problem asks us to graph 2 times cosine 4x cosine of x plus 2 times sine of 4x sine of x. And the first thing that I notice is that this whole thing is multiplied by 2. So I'm going to go ahead and pull that out. And then what I've got left is still pretty nasty, but I suspect that I will be able to find an identity which really simplifies cosine of 4x cosine of x plus sine 4x sine x. So I'm just going to consider 4x one of my angles, and then my other angle is going to be x. And I'm going to go down and look at my identities sheet and just see if I can find anything that's cosine times cosine plus sine times sine of 2 different angles. So looking down at my formula sheet, oh, yep, right here actually. This sum difference identity is right here. This is cosine of something times cosine of something plus sine of something times sine of something. And if you see it, this is a heck of a lot simpler than this over here. So we're going to make that swap to make the graphing easier. So I'm going to go back up to my problem, and I'm just going to bring my identity along with me so we can see it. But yes, in fact, that does match up really well. As you can see, it's cosine of something times cosine of something else plus sine of something times sine of something else. So in this case, let's see. Here's my x, and then this is my 4x. So really, all of this is going to simplify to be cosine of 4x minus x. Oh, and I forgot my 2 out in front. There we go. And that is pretty easy. That's just 2 times the cosine of 3x. And this will be much simpler to graph. It's really just a graph of cosine with 2 transformations. The transformations being, we're going to have to multiply it by 2. Let me move this out of my way. But we're going to have to multiply by 2, and then we will multiply our y values by 2, and then we will horizontally compress it by 1/3. So 2 times the cosine of 3x. Let me start with a regular cosine. So cosine starts at 1, and then it goes down to 0 at pi over 2. It's -1 at pi. It's 0 again at 3 pi over 2, and then it is 1 at 2 pi. So if I connect these with a smooth line, this is my original graph of cosine. Then I have to do two things. The first thing I'm going to do is deal with this 2, so I'm going to double all of my y values. Well, 1 doubled is just 2. 0 doubled, still 0. At pi, we've got -1. -1 times 2 is -2. 0 stays 0. And then over here at 2 pi, we've got 1. That doubled becomes 2. So here in green is 2 times the cosine of x. And the last thing I need to do is deal with this 3. So I need to take these x values and divide them by 3. So the first x value is going to be 0, and divided by 3 is still 0, so that point's not going to move. My next x value is pi over 2. Divided by 3, that's going to be pi over 6. That will be right here. Then this value is pi. Divided by 3, that's going to be pi over 3. That will move right here. This value is 3 pi over 2. Divided by 3, that's just going to be pi over 2. And that will be right here. And then my last one is going to be 2 pi divided by 3 becomes 2 pi over 3. That's right here. So I could continue this, but here is one cycle of it. Could probably have made that a little prettier. But if you wanted to keep going, it will just repeat the exact same pattern over again. And in total, I believe it will repeat 3 times. So in purple, my final answer is going to look something like this. And I like to label it final answer. Okay, moving on to the next one. We have another proof. So with our proofs, our strategy is always going to be find the more complicated side, and between algebra tricks and identities, make it look like the other side. So I'm noticing that this is a sum identity and a difference identity. I think this is supposed to be a capital B, by the way. But between the sum and the difference identities, I'm just going to go down and find those two and then see what I can swap out. So that would be these two functions right here. We've got our sum and difference identities for sine. So I'm going to copy that and bring it up with me to my problem. Here we go. So now, instead of sine of a plus b, I'm going to write the identity. That's the same as sine a cosine b plus cosine a sine b, which is exactly what's written over here. I just swapped out a and b. And then we've got plus sine a minus b, which is going to be sine a cosine b minus cosine a sine b. And then we're basically there, actually. This one, cosine a sine b, shows up twice. One's positive, one's negative, which means those two are going to cancel. These two are exactly identical, so they're going to combine because they're like terms, and we have 2 sine a cosine b, which is all that we're looking for, so we did it. For number 7, we are asked that we're told that tangent is equal to 3 and theta is in quadrant 1, so we're supposed to find the cosine of 2 theta. The first thing I'm going to do is find the cosine of 2 theta. Let's see. So cosine 2 theta, here we go. We've got multiple options. I can choose any one that I like. I'm going to choose one with cosine alone, just because I could have chosen the one with sine alone, but I just wanted one function. I didn't want two. This top one has 2 different functions, and I don't want to bother with that if I don't have to. So I'm just going to take the one that has a single function. It didn't really matter if it was cosine or sine, though. And then let's see. We've got this information. Cosine 2 theta is equal to 2 cosine squared theta minus 1. So what we're really going to need here is we're going to need cosine of theta is what we're looking for. The information we have now is tangent. Okay. Well, tangent is equal to 3. You know what I'm going to do is I'm going to draw a triangle. It's in quadrant 1. So let's see. Here is, let's call this length 1. We don't know what theta is, but it's in quadrant 1. And they said that tangent, which is opposite over adjacent, is equal to 3, which means the opposite is equal to 3 times the adjacent. So let's see. Because I want my hypotenuse to be 1, what I could do is I could swap out, instead of a opposite, I could write 3a right here. And then I could do this fact. I could say 3a squared plus a squared is equal to 1. And this a is my cosine, by the way, because adjacent cosine is adjacent over hypotenuse. So really cosine of theta is equal to a. I didn't have to call it a. I could have called it x or cosine or whatever. But I've called it a in this particular case. And then this equation will tell me exactly what it's equal to. So this gives me 9a squared plus a squared is equal to 1, which means that 10a squared equals 1, which means a squared is 1 over 10, which means a, or cosine, is 1 over root 10. And that is all the information that I need to plug into this formula. So I'm going to put that in right here. So cosine is 1 over root 10, and it's going to be squared. And from here, I can simplify a little bit. 1 over root 10 squared is 1 over 10. And then 2 times 1 over 10 is going to be 2 over 10, or just 1 over 5. And then for subtracting 1, that's going to end up being 1 over 5 minus 5 over 5, which is just negative 4 over 5. And that is the answer to this problem. Now, I will say it's uncommon, and because I've seen the test, I know what will be on there. It will be simpler than this. It is uncommon to be given tangent in this particular case. It is far more common to be given sine, cosine, secant, or cosecant. All of those would be a lot simpler. So if you had cosecant, for example, it would be really easy to change that to 1 over sine. So if you have cosecant, it's really easy to get sine. And if you had sine, you could use, well, I didn't copy it, but you might remember there was a third identity, and it's 1 minus 2 sine squared theta. So if you have sine, it's really easy to just plug that right in. So anyway, all that to say, this is the most complicated version of this problem. If you're given tangent, this problem is much, much simpler if you're given secant, cosecant, sine, or cosine, which is likely going to be the case on your exam. You'll be given sine, cosine, secant, or cosecant. Okay, for number 8, we're asked to graph again. And just like that last time, I'm noticing that both of these are multiplied by 2. So I'm going to go ahead and pull that out because it's not really necessary. And in fact, when I do that, I notice it's actually written immediately above us, 1 minus 2 sine squared theta. But just to be sure, I'm going to go down and look at my formula sheet, and I'm looking for this expression, 1 minus 2 sine squared theta. As a reminder, the reason I'm looking for this expression is it's very difficult for me to graph anything squared. Something squared is not a simple transformation. So I really want to avoid something squared if at all possible. So let's find an identity that looks like 1 minus 2 sine squared theta. And yep, there it is. And it is equal to the cosine of 2 theta, which is a lot simpler. Cosine of 2 theta is easy to graph. You just graph cosine and then you shrink it horizontally by 1/2. So I'm going to make this swap. 1 minus 2 sine squared theta is just, let me go back to my problem, is just equivalent to cosine of 2 theta. And I don't really need my parentheses, but it doesn't matter. And this will be nice and simple to graph now. All we have to do is graph cosine. Then we stretch it vertically by 2, and we compress it horizontally by 1/2, and that should be it. So the first thing I'm going to do is graph cosine, and that's like, oh, I'm not there. It's a 1, then 0, then -1, 0 again, and then back to 1. And I can connect those with a smooth line. Here's the original graph of cosine. Then I'm going to take care of this 2. So for that, I multiply every y value by 2. And there we go. It just kind of looks like this. And then this 2 here says that we're going to divide every x value in half. So 0 divided in half stays 0, so that point will stay. Pi over 2 divided in half will be pi over 4, which is unfortunately not on this graph, but I'm pretty sure it's right here. Then we've got pi, which divided in half is going to be pi over 2, and that will end up here. Then we've got 3 pi over 2, which divided in half is 3 pi over 4, and it's kind of hard to see where that is. I will do my best to make sure that you have an actually like a well-marked graph, but I'm pretty sure it's right here. Finally, you've got this point, which is 2 pi. Divided in half, it's going to be pi. And you will have this graph. And of course, it's just going to repeat. So if you wanted to sketch it a second time, well, it would end up something like this. And there we go. The purple is going to be our final answer. So this next question asks us to prove that cosine squared is equal to 1 plus cosine of 2x divided by 2. So what I'm going to do, as per usual, is focus on the more complicated side, which looks to me like this, and I'm going to swap things out until it starts to match this side. So the main thing that I notice is we've got a cosine of 2x over here and a cosine of x over here. And those are very different things. It is not easy to get back and forth between those two. So I'm going to look for an identity that swaps out cosine of 2x because I really don't want a cosine of 2x in here. I would like to get rid of that. So I'm going to go look at my identities. And the first place I'm going to look is going to be our double angle because that looks like a double angle. And yep, in fact, here it is. We've got cosine of 2x is equal to, and I don't really care exactly what it's equal to. I just noticed that it's equal to something with cosine. So that's the one I'm going to use right here. It says cosine of 2x is equal to, and I'm using this bottom one right here because the bottom one has a cosine of x alone, which is what the right side of this equation has. So this is going to be equal to 1 plus, and instead of cosine of 2x, I'm going to put 2 cosine squared x minus 1. And you may already notice, but that's going to simplify pretty easily because on top we've got a 1 plus and then a minus 1. Well, those two will cancel and we've just got 2 cosine squared x. And then we're going to have a 2 on top and 2 on bottom, which will also cancel. And we're left with just regular old cosine squared, which is exactly what we're looking for. For this next one, it says find the exact value, cosine pi over 12. And there are many ways to do this. You could do this with angle difference identities. I'm going to do it using half angle identity because I know the cosine of pi over 6. I know about the angle pi over 6, and this is really just pi of 6 over 2. So I'm going to go look for, let me see if I can write that clearly. There we go. I'm going to go look for an identity that tells me about angles divided in half because pi over 12 is just pi over 6 divided in half. And that will be my half angle identities right here. So cosine pi over 12, we're going to use this, which is cosine of theta over 2. Let's see. I'll put that here. So it's going to be equal to the square root of, well, let me make this a little bigger so I have plenty of room to work. 1 plus the cosine of pi over 6, because that's my theta, divided by 2. And let's see, cosine of pi over 6, that's going to be my 30-degree angle, which is this guy right here. And cosine is the x side, and it's the long one, which means it's going to be root 3 over 2. So we're going to have square root of 1 plus root 3 over 2, all divided in half. And we're going to be able to simplify this a little bit, but not a whole lot. This big square root's going to stay. On the top, I could combine these into one fraction. It would be 2 plus root 3 over 2. And then the whole thing's divided by 2. And then to combine those into one fraction, just divided by 2 is the same as divided by 4. But that's basically all I can do, so I'm going to leave it. This is going to be the answer for the exact value of cosine of pi over 12. For number 11, we're asked to graph 4 times the sine squared of x over 2. And this part right here, it's really the squared that's pretty nasty. Not something that we know how to graph with our current tools. So what I'm going to have to do is go to my identities, just like every other problem on here, and we're looking for sine squared of x over 2, or something that looks similar. And here we go. We've got sine squared theta over 2. That's exactly what we want. So I'm going to take that one and move it up here. And let's see, sine squared of x over 2. Well, the 4 is going to stay out in front. So we've got y is equal to, the 4 stays, but instead of this piece of it, we're going to use this identity. And we're going to have 1 minus cosine theta over 2. And then you might realize that we've got a times 4 and divided by 2. So that's really the same as just 2 times 1 minus cosine theta. And I'm running out of space, but that's just 2 minus 2 cosine theta. So what I'm going to have to do is graph cosine. I'm going to have to flip it upside down. That's what this negative will do. I'm going to stretch it vertically by 2, and then I'm going to add 2, which means move it up vertically. Actually, let me rewrite it like this. It's just a little different, but it'll be negative 2 cosine theta plus 2. That's written in a little more familiar way, so we're going to use that form to graph it. So let me make this smaller, move it over so I can have plenty of space. And let's see. Let's start with the graph of cosine. Well, that's this. 1, 0, negative 1, 0, back to 1. Connect it with a smooth line. Hopefully this is familiar. And then we're going to... Well, we're going to do 2 things. You can do them separately or at the same time, but we're going to double every y value, which ends up like this. Here's my new graph. And then this negative out in front will flip everything upside down. So it ends up like this. And let's see, every y value is doubled. These are not the smoothest lines I've ever drawn, but whatever. And then the last thing we're going to do is move it up to, and unfortunately, actually, it looks like we do not have enough room on this graph to do so, because this point's going to move up here, my 0 is going to move up here, and it's really this guy that's going to move way up there. So I will do my best to make sure that you don't encounter this problem on the test. Let me see if I can make this smooth and pretty. I'm going to do one side at a time. There we go. That's all right. Nope, I can do better. Something like that is going to be my final answer. And if you encounter this problem on the test where you don't have enough room, you can handle it the way I have, where I just kind of extend the graph. I'm not going to be picky about it. Or you are welcome to relabel these numbers if you prefer. I'll do my best to make sure you don't encounter this situation. Okay, for number 12, same strategy as normal. We're going to work on the more complicated side, and we want to swap things out until it looks like this side. So there's a lot of things that we could do with this one. There's many ways to do it. But what I'm noticing is that we have a lot of different functions over here. We've got tangent, we've got sine. Well, I guess we got 2 different functions, but still. Let's see if the first thing I'm going to try to do... The first thing I'm going to try to do is to reduce it into maybe just one function. So I'm going to rewrite this. Instead of tangent, I'm going to do cosine over sine. And then this will be sine over 1, cosine. No, it's sine over cosine. What am I doing? Sine over cosine. There we go. Tangent is sine over cosine. Yeah. And then let's see. To combine these fractions, I'm going to do this. Because what I want to try to do is simplify as much as possible. So this will be sine plus sine times cosine, all over cosine, all divided by 2 sine theta over cosine theta. Ah, yes, this is what I wanted. Now you may notice cosine will cancel, which is better. Now we've got sine theta plus sine theta cosine theta over 2 sine theta. And the next thing I notice is that every single thing in here has a sine in it. So I really could, well, let me factor it out of the top. This is the same as sine theta times 1 plus cosine theta over 2 sine theta. And now that it's factored, it cancels on the top and bottom, and we have 1 plus cosine theta over 2, which is much better. 1 plus cosine theta over 2 is a lot easier to manage than what I had before. So the last thing I'm going to do is I need an identity to get me from here to here, and I suspect it's going to be immediate. So I'm going to go down and look at my identities. We've got 1 plus cosine over 2. And yep, here we go. 1 plus cosine over 2 is equal to the cosine squared of theta over 2, which is exactly what we were asked to prove. So I'm going to use this identity, and I'm going to say that this function is equal to cosine squared theta over 2. And we're done. All right, number 13 has asked us to rewrite it as a sum or difference and simplify if possible. So we have a sine of some angle times a cosine of some angle, and this 10 will just stay out in front. So if you like, you can consider this as 10 times something. So the first thing I'm going to do is go down and look at my identities. I'm looking for sine of something times cosine of something. And they want us to rewrite it as a sum or a difference. Well, to do that, I'm going to use the sum and difference identities. Or excuse me. No, I'm going to use the sum to product or product to sum. So let's see. I think it's going to be this one down here. We've got sine times cosine. I'm going to use this identity right here. And if I go up, let's see. Yep, sine times cosine. Here we go. In this case, sine is going to be, 5x is going to be our theta, and then our other angle will be 3x. So this will all be equal to, I'll leave the 10 out in front, and let me write down whatever's left. It'll be sine of the two angles added together, so that's sine 5x plus 3x, plus the two angles subtracted, so sine of 5x minus 3x. And then it's all divided by 2. Yeah, so I can simplify this a little bit. Let's see. The 10 and the 2, that'll cancel, and it'll just be 5. And then it'll be sine of 8x plus, 5x minus 3x is just going to be 2x. And then I could distribute the 5, and I end up with 5 sine 8x plus 5 sine 2x. And that's it. That's all it asks us to do. It is now a sum, and we are finished. Number 14 is going to be very similar. We're going to have a cosine minus a cosine, and we're supposed to rewrite it as a product. So I'm going to go down to my sum to products. There we go. It's going to be this one right here because it's cosine minus cosine. and we will really just plug it in. So we've got 5x is our first angle, and x is our second angle. And it's going to be equal to -2 times the sine of, and then this piece is the two angles added together. So that's 5x plus x over 2. And then sine of the two angles subtracted. So it'll be 5x minus x over 2. And then I can simplify this a little bit, but let's see. 5x plus x is going to be 6x. And then 5x minus x is going to be 4x. And if I simplify that even a little bit further, I get -2 times the sine of 3x times the sine, oops, I wrote sine x and I really just meant sine. There we go. -2 sine of 3x times the sine of 2x. And that is it. This is as simple as it gets, so we are finished. All right, number 15. As always, strategy is work on the more complicated side. This is a lot of angle sums. It's multiple different functions. We've got sine of 3x, sine of x, cosine of 3x, cosine of x. That's a lot of different things. And I know that there's no identity for sine of 3x or cosine of 3x. If it had been 2x, I might think of the double angles, but there's nothing for sine of 3x. So what I'm going to use instead is going to be the sum to product formulas. So I'm going to look for sine plus sine and then cosine minus cosine. And if I do that, let's see. Yeah, so we're going to use this guy right here, sine plus sine. And let me move it up. That's what we'll use on on the top of our fraction. And then we've got cosine minus cosine, which is this guy. And that is what we will use on the bottom of our fraction. So with these two in mind, I'm going to rewrite the top as 2 times the sine of, and it's this, so it'll be the two angles added, which is 3x plus x over 2. And then cosine of 3x minus x over 2. And then it's all divided by, and then I use this one on the bottom, -2 sine 3x plus x over 2, and then sine 3x minus x over 2. From here, I can just simplify a little bit. Let's see. These 2's will cancel. And then actually, I noticed that this is exactly the same as this. So I could simplify them, but I don't have to. I can just cancel them. They're identical, and they're multiplied on the top and bottom, so they go away. So I end up with this cosine. And let's see, 3x minus x is just 2x. And then on the bottom, I have this negative, and then it's a sine. And again, 3x minus x is just 2x. And I can simplify this a little further. This will be cosine of x over negative sine of x. And hey, I know that cosine over sine is cotangent. And that is exactly what I was looking for, so we are finished. So problem number 16 asks us to solve an equation. And the good news is we're only asked to solve it within the actual unit circle. So this equation is actually reasonably straightforward because we already have one single trig function, which is usually our goal. If we have multiple, we want to condense it into one. But this already has one, so all we're going to need to do is get it by itself. So to get it by itself, we're going to add this √3 to both sides. And we'll have 2 cosine x equals √3. And then I'm going to divide both sides by 2. And I have cosine of x is equal to √3 over 2. Then all I have to do is think about my unit circle. Where in my unit circle is cosine equal to √3 over 2? Well, if you want to draw a quick sketch, you can. Cosine is positive in this quadrant and this quadrant. And really, it's these two angles. And I know it's these two angles because √3 over 2 is the long side of a 30, 60, 90 triangle. So if it's a 30, 60, 90 triangle, I know this is 30 degrees and this is -30 degrees, which really just means that it's 330. So that'll be the answer. X is 30 degrees or 330 degrees. For number 17, again, the goal is to do one of two things. You either condense all of your trig functions into a single trig function, or you split up your equations so that they're isolated. And in this one, I noticed that this will factor very nicely. So I'm going to factor out a sine x. And then it's really easy to split it. If two things multiplied equals 0, that means that sine x equals 0, or 1 plus 2 cosine x equals 0. From here, I just have to think about where this is true. Well, sine of x is equal to 0 at 0, and then it'll also be equal to 0 at pi. And for both of these, actually, I'm going to list them separately. Actually, no, you know what? Here's how I'm going to think about it. As I move around the unit circle as many times as I need, sine will be equal to 0 anytime I hit this point and this point. So if I add pi every time, it's always going to be equal to 0. So it's really just 0 plus pi k. And that's just the same as saying pi k. Now, if you had written 0 plus 2 pi k and then pi plus 2 pi k, this is also correct. It's the same thing. This is just the simpler way of writing it. So this is saying start at 0 and add 2 pi. And this is saying start at pi and add 2 pi. As many times or as few times as you want. And the simpler way of writing that is just literally take pi as many times as you want. So I would accept either of those answers. The one in black is simpler, but both are correct. For this one, the goal is going to be to get the cosine by itself. So first thing I'm going to do is subtract 1 from both sides. And then I'm going to divide both sides by 2. And I get that cosine x equals -1/2. And there's going to be two different angles in the unit circle at which this is true. So just like last time, I'm probably going to draw a quick sketch. If the cosine is -1/2, that's like this or this. And a half is the short side of a 30, 60, 90 triangle, which means that this angle is 60 degrees, which means that this is 120. Oh, but it asked for radians, didn't it? Yep, it asked for radians. So instead of degrees, it's going to be, let's see, this will be pi over 3. So this is 2 pi over 3. And then this one is going to be 4 pi over 3. So those are my two answers. X is 2 pi over 3, or X is 4 pi over 3. And for both of these, we're allowed to add and subtract 2 pi as many times as we want. So I'm going to add 2 pi k. And this is as simple as this answer is going to get. This is the correct final answer. I can't combine them into one because they're not evenly spaced. Back over here, 0 and pi are evenly spaced. You add pi, you get here. You add pi again, you get back to there. They're evenly spaced. These two are not, and you can tell that visually. To get from one to the other, do you see how the two distances are very different? We've got a short distance and a long distance. So because those two distances are not equivalent, there's no way to condense it. This is the final answer. So this next problem asks us to solve 2 sine squared x minus 2 sine x minus 1. And the good news here is that it is already in terms of a single trig function. These are both sine of x. One is squared and one is not, but that just means we're going to treat it like a quadratic, because this looks exactly like a quadratic. 2 times something squared minus 2 times something minus 1. So in this case, this is going to be A, and this will be B, and this will be C. And normally we have x equals, and this is sine of x instead of regular x, but otherwise it's exactly like a quadratic. So we're going to use our quadratic formula. Sine of x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And in this case, that's going to be 2 plus or minus the square root of Negative 2 squared is 4. Then we've got 4 times 2 times negative 1 all over 2 times 2. And we can simplify that a little bit. Let's see, 4 minus 4 times 2 times negative 1, that'll be root 12 over 4. And then let's see, 2 plus or minus root 12 splits into root 4 times root 3. And that's just 2 plus 2 root 3 over 4. And then everything in here divides by 2. And we end up with 1 plus root 3 over 2. Now this is not a number that's on our unit circle. So to find where sine is equal to this, we're going to have to use, oh, I keep writing just plus. It needs to be plus or minus. There, plus or minus. We're going to have to do inverse sine of 1. Well, actually, I'm going to think about this for a second. 1 plus root 3 over 2. You can put in your calculator, but it's going to be greater than 1, which means this will have no solutions. If you typed into your calculator inverse sine of 1 plus root 3 over 2, you will get error. There's no such thing as an inverse sine for a number greater than 1. So you could try typing it in, you will get a problem because it's bigger than 1. So I'm going to move on to just the minus version. And when I put that into my calculator, let's see, I think I already did. And yes, inverse sine 1 minus root 3 over 4 is going to be negative 10.5 degrees. And let's see, that is just the reference angle. So let me draw a quick sketch. That's like right here. But the other place it could happen is right over here. So it's actually going to be, let's see, I'm going to say x is approximately equal to, well, instead of a negative, let's do it as a positive. So 360 minus 10.5 is going to be 349.5 degrees. And then this one right here will be 180 plus 10.5. So x is also going to be approximately equal to 190.5. And that should mostly be it. Both of these we can put plus 360k because we can add or subtract 360 as many times as we want. But other than that, this is it. All right. Number 19, we have two different trig functions. We've got a sine of x and a cosine of 2x. So the first thing I'm going to try to do is swap one of those out. So I'm going to go look at my formula sheet. And on my formula sheet, I know, well, I see this one in particular, cosine of 2 theta, and it's equal to 1 minus 2 sine squared theta. So let me show you why I picked that one. We've got a cosine of 2x here, cosine of 2x here, and then the other trig function we have in this equation is going to be sine. So I'm looking for something that has just sine. So I do not want to use this one because it's got both cosine and sine. I do not want to use this one because it's just got cosine. Really, this is going to be my best option. So my equation changes into 1 minus 2 sine squared x minus 3 sine x minus 2 equals 0. And I'm going to move this so that I have some room to work. But this will simplify a little bit into, let's see, we've got a 1 and then a minus 2. So these two become just negative 1. So I've got negative 2 sine squared x minus 3 sine x minus 1 equals 0. Then I can just, you don't have to, but I can divide everything by a negative, so I'm going to. Now this is, again, a quadratic. So from here, I'm going to use my quadratic formula. And I've got sine of x is equal, well, let's label out my pieces. This is A, this is B, and this is C. So I will have x equals negative b, well, not x, sine of x equals negative b plus or minus the square root of, and then b squared is 9 minus 4 times 2 times 1 all over 2 times 2. And let's see, this will simplify to be negative 3 plus or minus 9 minus 8 is just going to be 1. Square root of 1 is still 1, so it'll be negative 3 plus or minus 1 over 4. And then I'm going to split these into 2. So I've got sine x equals negative 3 minus 1 over 4, or sine x equals negative 3 plus 1 over 4. This one becomes negative 4 over 4, which is just negative 1. And in the unit circle, sine is negative 1. Let's see, it'll be here. Negative 1 at 3 pi over 2. And it only wants us to solve angles inside the unit circle, so 3 pi over 2 is the only one that will answer that. This one is negative 3 plus 1. That's negative 2 over 4. That's negative a half. And sine is negative a half in two places. I can draw a quick sketch, but it would be like here and here. And let's see. This piece right here is going to be pi over 6. So this one will be 7 pi over 6. And this one will be 11 pi over 6. So those are my two values. X equals 7 pi over 6 or 11 pi over 6. And those should be the answers to this equation. I'm going to move this previous one up so it's clear that it belongs with the previous problem. There we go. Okay, number 20. Again, we've got two different trig functions. We've got a cosine and a sine squared. Well, cosine and a sine. Coincidentally, the sine is squared. My goal is always to get everything in terms of a single trig function, and off the top of my head, I know that there's a good relationship between sine squared and cosine squared. Specifically, this sine squared is 1 minus cosine squared. So I'm going to use that and plug this in right here so that everything will be in terms of cosine. So I'm going to have 2 times 1 minus cosine squared of x minus cosine x minus 1. And then I can simplify this. This is 2 minus 2 cosine squared x minus cosine x minus 1, which is negative 2 cosine squared x minus cosine x minus 1 plus 2 is going to be plus 1. And then I could, although it's not necessary, divide everything by a negative. Now again, this looks like a quadratic, so I'm going to solve it like a quadratic yet again. Here's my a, my b is 1, and my c is negative 1. So I'm going to have cosine of x is equal to, let's see, negative b plus or minus the square root of b squared is going to be 1 minus 4 times 2 times negative 1, all over 2 times 2. And let's see, 1 minus, which just becomes plus because that negative, oh, this will be root 9 over 4, which is negative 1 minus 3 over 4, or negative 1 plus 3 over 4. And negative 1 minus 3 is negative 4. That simplifies to be negative 1. And this negative 1 plus 3 is going to be, it's 1/2. It's 2 over 4, 1/2. Okay, and then it says 0 to 2 pi. So we're really only looking for angles in the unit circle. So for this one, cosine is negative 1 at pi. And for this one, cosine is, well, I can draw a quick sketch if I want. If cosine is a half, that's here or here, because x is the short side of a 30, 60, 90 triangle, which means this is pi over 3. So one of them is pi over 3, and the other one is going to be 5 pi over 3. And that should be it. Those are my two answers. All right, 21. This is exactly the same as the previous one. We've got two different trig functions. We've got a sine and a cosine. We're going to use the exact same identity as we did in the last one. Sine squared theta is 1 minus cosine squared theta. And we're going to do that because our goal is always get it in terms of a single trig function. Or, That's one of the two options. The only other option is to split it into two separate equations. So if we could have factored out this sign, that would have been a good option. But obviously these don't have sign in it, so it will not factor out. So we can't factor it, so we have to swap it. Which is exactly what I did here. And then just like the last one, we're just going to simplify a little bit. Let's see. Then we can combine our like terms. We've got -4 cosine squared theta plus 4 cosine theta. -5 plus 4 is going to be -1. Not really necessary, but I'll divide everything by a negative just because I like to. And there we go. Now we've got, this is A, this is B, this is C. So cosine of theta is going to be -b plus or minus the square root of, let's see, b squared is 16 minus 4 times 1 all over 2 times 4. And let's see, this square root is going to end up being 0. So we're going to have 4 plus or minus 0 over 8, which is really just 1/2. And that's the only valid answer to this. So to solve it for all radian solutions, cosine theta is equal to 1/2. Well, in the unit circle, it happens in two places. So I like to draw a quick sketch. That's here and here, where x is the short side of a 30, 60, 90 triangle, which means this, and it says radian. So this is pi over 3. This is negative pi over 3, which is just the same as 5 pi over 3. So those are going to be my two angles. Theta equals pi over 3, or theta equals 5 pi over 3. And then because it says all radian solutions, I'm just going to stick a plus 2 pi k to both of these. And that should be it. All right, for this next one, we are starting off with a lot of trig functions. We've got sine of 2x, cosine of x, cosine 2x, sine of x. That's a lot of different trig functions, and it looks pretty nasty. So what I'm going to do is look at my identities and see if there's an expression that looks like this that reduces all the way down to a single trig identity. And I suspect it's very likely there will be one. We've got, let's see, sine of something, cosine of something, plus cosine sine. So sine, cosine, plus cosine sine. And yep, I see it already. Here we go. Sine, cosine, plus cosine sine. It will simplify all the way down into just regular old sine. So let's see, right here, just to highlight, we've got 2x is our theta, our first angle, and our second angle is just going to be x. So all of that is really equal to sine of 2x plus x, which is indeed much, much simpler. And sine of 2x plus x, well, that's just the same as saying sine of 3x is equal to 1/2. And we're already nearly finished with this problem. So the next question is, where is sine equal to 1/2? So I like to draw a sketch, and let's see. Sine is y is 1/2, either right here or here, where it's the short side of a 30, 60, 90 triangle. So this is going to be, what did it say? We're in radians, so this is pi over 3, and this one is going to be 2 pi over 3. So we've got 3x is pi over 3, or 3x is 2 pi over 3. Now, for the record, it could also be like, you could do plus 2 pi, so it could also be pi over 3 plus 2 pi, or you could do plus 4 pi, whatever. You can make a list of a lot of different things. And the reason to do this is just to make absolutely sure that you have gotten all possible values. But plus 2 pi will not change the angle. Plus 4 pi will also not change the angle. I'm going to simplify each of these. Let's see, this is 7 pi over 3. And this is, let's see, 13 pi over 3. And this is 8 pi over 3. And this one is, oh, I forgot already. 14 pi over 3. Okay, the last thing I'm going to do is divide every single one of these by 3. For the record, there's more than this. I don't need to list all of them, though. I'm just trying to get everything that will end up being between 0 and 2 pi. From this, I get x equals pi over 9, 7 pi over 9, 13 pi over 9, and I think that's going to be it. If I had done one more, the one more would be, I think it would be too big. Yeah, it would be bigger than 2 pi. So then one below gives me 2 pi over 9, 8 pi over 9, and 14 pi over 9. And yeah, if I had done one more, this would be, let's see, 19 pi over 3, and then divided by 3 is 19 pi over 9, which is bigger than 2 pi, so I don't need it, because we only want the ones that are less than 2 pi. So I've got all the ones that are less than 2 pi. This is the answer. This next question asks us to solve sine squared of 4x is equal to 1 for all radian solutions. There's many ways to do this. You could subtract 1 from both sides and then treat it like a quadratic. But also, I'm noticing that I could just take the square root of both sides. As long as I think about plus or minus, that should work perfectly. So if I do that, I end up with sine of 4x is equal to 1, or sine 4x is equal to negative 1. And no matter what you had done, if you had subtracted 1 from both sides, treated it like a quadratic, factored it, whatever, you would end up here. I think square rooting is the fastest way to get there, though. Anyway, from here, I'm just going to ask myself, where is sine equal to 1? And sine is equal to 1 at a pi over 2. And sine is equal to negative 1 at 3 pi over 2. And this is one of those cases where they're evenly spaced. Here, I'll draw a quick sketch. So really, it's here and it's here. So you might notice they are evenly spaced. So we could just put plus pi and combine them into 1. So let me write that out. It's possible to write it like this, plus 2 pi k plus 2 pi k. Or if you want to combine it into 1, it would be 4x equals pi over 2 plus pi k. And that works, again, because they're evenly spaced. They are both plus pi away from each other. Now, I'm basically done. The only other thing I have to do is divide everything by 4, and that gives me x equals pi over 8 plus pi over 4k. And that's it. That's the answer to this question. This last one asks me to solve. It looks vaguely like a quadratic, but we do have two different trig functions. We've got a cosine and we've got a sine. But the nice thing is the angle is the same. They're both of 2 theta. So I'm going to use this fact. Sine squared of anything, it could be 2 theta, is equal to 1 minus cosine squared of the same thing. So that fact will get me this. I'm going to have negative 2 times 1 minus cosine squared, 2 theta, minus cosine 2 theta, plus 1 equals 0. And then I can distribute this negative 2. And then we'll do a little bit of simplifying, but you might already notice this looks like a quadratic. So we're going to have 2 cosine squared of 2 theta minus cosine of 2 theta. And then plus 1 minus 2 is just going to be minus 1. Here, it's a quadratic already. We've got a times something squared. B is negative 1. C is also negative 1. And the thing that is squared is just cosine of 2 theta. So cosine of 2 theta is going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. And that is, let's see, 1 plus or minus 4 times 2, oh, this will be root 9, which is 1 plus or minus 3 over 4. So we're looking for two cases. Cosine 2 theta is equal to 1 plus 3 is going to be 4 over 4, or 1 minus 3 is going to be negative 1/2 equals negative 1/2. Well, cosine is equal to 1 at 0, and it says for all radian solutions, so I'm going to put plus 2 pi k. And then over here, cosine is equal to negative 1/2. Well, that happens in my unit circle. Let me draw my quick sketch. That happens here and here, which is 2 pi over 3 and 4 pi over 3. So those are the two answers here. And then with both of these, I'm going to put plus 2 pi k because it said for all radian solutions. And my final step is to divide every single one of these by 2. And when I do that, I get the answer theta equals pi k, or theta equals pi over 3 plus pi k, or theta equals 2 pi over 3 plus pi k. And that should be it. Those are all the possible answers. So this next question asks us to graph x equals cosine of 2t and y equals cosine of t, which is a parametric equation. And it says to do that by plotting points. So what I really like to do is just make a little table. And my table is just going to be values for t, and then I'll plug it into x, and I'll plug it into y. So I'm going to choose some convenient values to plug into t and cosine of 2t, to cosine of t and cosine of 2t. So first one's obviously going to be 0. That's a pretty easy one. And then I'll probably try pi over 4, and then like pi over 2. Then I might do 3 pi over 4, and then, no, wait a minute. Do I want to do that? Yeah, pi over 2, 3 pi over 4, and then I'll do pi. And then I think I can actually stop there. I'm pretty sure it's going to start repeating at that point in some sense. I could keep going, but I think this will be enough for me to get the general shape. So let's see. If I plug in 0, I get cosine of 0 and cosine of 0, which is going to be 1 and 1. So I'm going to plot that point. X is 1, y is 1. That's right here. Then my next point, let's see. I've got pi over 4. So if I plug that in right here, I get cosine of 2 times pi over 4. That's just pi over 2. So the cosine of pi over 2 is going to be 0. And then the cosine of pi over 4 is root 2 over 2. Then the next one I'm going to plug in is pi over 2. So if I put that right here, that gives me pi. So cosine of pi is negative 1. And cosine of pi over 2 is going to be 0. Then on my next value, let's see, 3 pi over 4, but I plug it in here, I get 3 pi over 2, which is going to give me cosine of 3 pi over 2 is 0. And then cosine of 3 pi over 4 is going to be negative root 2 over 2. And then my last one is cosine of 2 pi is going to be 1. And cosine of pi is going to be negative 1. So if I plot all those points, let's see, root 2 over 2 is like roughly 0.7. So that's like here. And then negative 1, 0 is right here, here, and here. Connecting those with a smooth line gives me a parabola, actually, which you can tell by using identities, but we were just told to plot it using some points. So this will be the final answer. So problem 26 asks us to eliminate the parameter. So that really means we want to come up with an expression that relates x and y that does not include t anymore. T is the parameter. We're trying to get rid of it. So the strategy that we showed before is 2 steps. The first step is to isolate the trig functions. And the second step is going to be plug them in to an identity. And it's specifically just any identity that relates the two trig functions. So in this particular case, our two trig functions are going to be secant of t and tangent of t. And what may come to your mind, what hopefully comes to your mind, is one of the Pythagorean identities, specifically this one. 1 plus tangent squared of something is equal to secant squared of something. And we could rearrange this a little bit. We could also write this as 1 equals secant squared t minus tangent squared t. It doesn't really matter which way you write it, but this is the identity that I'm going to plug them into. So to follow these two steps, the first thing I really need to do is to isolate the trig function. So I've got x equals 2 plus 3 tangent of t. So what I'm going to do is subtract 2 from both sides. And I have x minus 2 equals 3 tangent of t. And then I'm going to divide both sides by 3. And I end up with tangent of t is equal to x minus 2 over 3. So it's been isolated. For the other one, it'll be very similar. I've got y equals 4 plus 3 secant of t. Same idea. First thing I'm going to do is subtract 4 from both sides. And I have y minus 4 equals 3 secant of t. Then I'm going to divide both sides by 3. And then I end up with secant of t is equal to y minus 4 over 3. So my last step is going to be to plug these two expressions into this identity over here. So I'm going to have 1 equals, and then instead of secant, I'm going to put y minus 4 over 3. And I'll square it because it's squared in the identity. And then it's minus, and again, instead of tangent, I'm going to put in x minus 2 over 3, and again, it's squared. And this is actually all I need to do. I have successfully eliminated the parameter. This is a relationship between x and y that no longer depends on t. For 27, we're asked to do something very, very similar, but there's a follow-up step that is to sketch the graph of the curve. So I'm going to follow the exact same two steps. So the first thing I'm going to do is isolate these trig functions. So I've got x equals 2 plus sine of t, and y equals 3 plus cosine of t. So with both of these, to isolate the trig function, I'm just going to do minus 2 over here, and I'll do minus 3 over here, and I end up with x minus 2 equals the sine. And then here I have y minus 3 equals the cosine. And that is it. They are already isolated. So if I were to ask you what's a good identity for relating sine to cosine, hopefully what comes to your mind is this. Sine squared plus cosine squared is equal to 1. The vast majority of the time, the relationships for these eliminate the parameter problems are going to be the Pythagorean identities. So if you know your 3 Pythagorean identities, that's probably what you're going to use here. But in this case, instead of sine, we're going to have x minus 2. So it'll be x minus 2 squared, and then instead of cosine, we've got y minus 3, and it's equal to 1. Now, if you remember, this is actually the equation of a circle. Specifically, it's a circle with a center, and the center is at 2, 3 from this 2 and this 3. And it is a circle with a radius of 1 because you take the square root of this side to get the radius. So that is how we're going to sketch it. We're just going to draw a circle that has a center at 2, 3. So let's see, 2, 3 is right here. And then a radius of 1. Well, I think 1 is like 2 squares here. So the radius, 1, will go out this far. So this is going to be my circle. Center 2, 3, radius 1. And that should be my final answer.